Good afternoon, everybody. Welcome to Parsons Technical Webinar Series. I'm your host, Jessica Bennett. Today we have Kristen Brooks with us, presenting on MGP-Impacted sediment, overcoming unique challenges during remedial design and construction. A few housekeeping items up front. We'll have all phone lines muted during the presentation until the Q&A at the end to keep background noise down. If you have any questions throughout the presentation, you can either hold on to them and ask live at the end, or you can enter them into the chat feature at any time. This webinar has been approved for 1 PDH credit. If you'd like to receive a certificate for attending today, you can download the form that will be available at a URL link we'll post in the chat. There are 4 questions you'll have to answer that are multiple choice, so please take a chance to look at those. We'll also post those in the chat throughout the webinar so you can quickly reference to them. And please let us know if you have any issues getting this form if you'd like to get a certificate. And finally, this webinar is being recorded and will be posted on our YouTube channel in the next few days. So just a brief agenda, I'll introduce the guest speaker today, Kristen Brooks. She'll present on the core value moment, and then will be the technical presentation, followed by a Q&A session at the end of the presentation. Kristen is an environmental engineer, experienced with a wide variety of environmental remediation projects, including contaminated sediment, landfills, and in-situ solidification. Her work focuses primarily on remedial designs, permitting, and stormwater management. She has a Bachelor's of Science in Biochemistry and Geology from SUNY Buffalo, and a Master's of Science in Environmental Engineering from Virginia Tech. And with that, I'll turn it over to Kristen for the core value moment.
So good afternoon, everyone. So here we're just seeing the 6 core values that we have here at Parsons. Today, I'm going to talk about safety. So March is Eye Safety Month. More than 2,000 eye injuries occur on the job every day. About 10% of these result in lost time. 10 to 20% of these can cause temporary or permanent vision loss, and nearly 40% of these eye injuries occur in settings where you might not necessarily expect an eye injury to occur, so in an office, a healthcare setting, or a laboratory. In order to prevent eye injuries, it's important to always wear appropriate safety eyewear for a given job site, even if you're only briefly going to be within a hazardous area. So in an area where there might be particles or dust, wear safety glasses with side shields. Wear safety goggles or face shields to protect against splashing when you're working with chemicals. And wear special purpose safety goggles or helmets when you're working around hazardous radiation, so welding or fiber optics. So I'm going to provide an introduction to this talk and a brief agenda for the talk as well. So I'm going to start this talk by providing a background on what a manufactured gas plant is. I'm going to talk about remediation of MGPs within New York State. I'll talk about some challenges that are specific to remediating sediment at MGP sites. Then I'm going to talk about 2 different sites that Parsons has been involved in that are former MGPs. The first one is the West Station former MGP, where Parsons performed the remedial design. This site is scheduled to go to construction within the next few months. I'll provide some background on this site. I'll talk about our design approach for the upland and the in-water components of this site. I'll talk about how the overall system of the site works and some construction sequencing considerations. And then I'm going to talk about the Saranac Street former manufactured gas plant, where Parsons has served as the construction manager for the last couple of years. Again, I'll give some site background. I'll talk about some alternative site investigation methods that were used here. I'll talk about some different diversion systems that have been used here as well, how some different historical structures have factored into the work done at the site, and some environmental and public safety controls. So a manufactured gas plant is a facility that was used to process coal into manufactured gas used for lighting, heating, and cooking. There were 2 main processes used to manufacture gas. The older and simpler process was coal carbonization, in which coal was heated in closed retorts or beehive ovens. Volatile constituents of the coal would be driven off as a gas, which was collected, cooled, and purified prior to being piped into the surrounding areas for use. As the MGP industry developed and expanded after the Civil War, a new process was introduced which produced a gas mixture that burned hotter and brighter. This process is known as carbureted water gas and was first introduced in the 1870s. By 1900, most MGPs in New York State were using this new process. There were a variety of water gas processes developed. All of these started by heating coke or coal in the presence of steam. This first step produced a flammable gas mixture of methane and carbon monoxide. Then this mixture had petroleum products sprayed into it, which created more methane. That in turn increased the heating and lighting value of the gas. These facilities often required water to operate, so they were often located along shorelines, and they generated several waste products, including coal tar and purifier waste. Coal tar is a dense, oily liquid that would condense out of the gas during production. Most of the coal tar was typically recovered, but some tar would leak out of the system or would be discharged, typically as a mixture of tar and water, and this can result in contamination of soil, groundwater, and surface water. Within a surface water body, tar typically will sink to the bottom, so that can also result in sediment contamination. Purifier waste is typically composed of either lime or wood chips treated with iron oxides. This was used to remove sulfur and cyanide from manufactured gas. This waste was often used as a fill material, so that results in soil and groundwater contamination at these sites. The specific chemicals of concern that tend to be present at MGP sites are polycyclic aromatic hydrocarbons, or PAHs, the volatile organic compounds BTEX, which are benzene, toluene, ethylbenzene, and xylenes. It's also pretty typical to see some heavy metals like arsenic, lead, and mercury, and cyanide is also a pretty typical contaminant. I'm going to use the term NAPL a lot during this presentation. This is an acronym for non-aqueous phase liquid. It refers to organic compounds that are not miscible with water, and this material is often the target of remediation since a lot of these chemicals of concern are constituents of NAPL. So MGPs have been used in New York State for nearly 150 years. The first site was a plant in New York City that was built in 1826. This was a demonstration plant that produced gas from whale oil. The last active plant closed in 1972, but most had closed by the 1950s. This was partially because as natural gas became more widely available, manufactured gas was less necessary. Within New York State, there have been more than 200 MGPs located, and it is estimated as many as 300 may exist. The New York State DC's current best estimate is about 260 of these sites. Nationally, there is an estimated 3,000 to 5,000 of these sites. Some MGPs were very small and would just provide gas for an individual factory or institution, so that contributes to not necessarily knowing where all of these facilities existed. Remediation efforts began in the 1990s. These were generally performed by major utilities that own the former plants, with oversight by the New York State Department of Environmental Conservation. Many sites are currently undergoing remediation at varying stages. Remedial programs are currently underway or scheduled to start at 240 MGP sites in New York. So there are some challenges specific to performing the sediment remediation at former MGP sites. Some of these challenges during the investigation phase include locating bedrock or confining surface. Also locating the extent of impacts can be challenging. During the design phase, some different historical structures like dams or drains can complicate the design. And during the construction phase, there are some challenges associated with dewatering the area you're going to be working in, and also with preventing the generation or spreading of turbidity, sheen, and odors. Sheen and odors are pretty typical at MGP sites, and turbidity is going to be a concern anytime you're working within sediment. So next I'm going to talk about the West Station former MGP site, which is located in Rochester, New York. So this site was operated from about 1910 until 1952. It was used as part of a large coal-fired power generating facility from 1952 until 1999. That station was removed from service in 1999 and then demolished in 2017. The site is currently vacant. It's located within the Genesee River Gorge, and it's under an order of consent to be remediated under the State Superfund program. It's on the west bank of the Genesee River and is comprised of two typical portions. So there's an upland portion of the site that is flat and vacant, about 5.5 acres. This large open area has a lot of space for construction water treatment, sediment processing, and material and equipment laydown areas. So that's going to be very valuable during construction at the site. Then the river side of the site is located adjacent to the river. That's separated from the upland portion of the site by a concrete retaining wall. In this most downstream or most northern portion of the site, located around in here, there's a lower profile stone retaining wall in the more upstream portion of the site here, and there's some additional infrastructure as well as the wall of the gorge that separates the two portions of the site more towards the middle. So the major remedial components of the site are removal of contaminated sediment and soil and protecting the river from future migration of NAPL from the upland portion of the site to the river. So we'll be excavating in these 3 areas shown. The sediments tend to be pretty coarse, so we have a lot of cobble and gravel type sediments, some areas of exposed bedrock as well. All 3 of those areas include both sediment removal and bank soil removal areas. In order to prevent NAPL migration from the upland portion of the site to the river, we'll be sealing openings in the existing concrete retaining wall, extending a low permeability barrier, so that ISS wall, and adding passive NAPL recovery wells. The remedy also includes some restoration, which will include placement of a soil cover. So this slide shows a schematic demonstrating how the overall site can be conceptualized. So within all 3 excavation areas, there will be a barrier wall structure separating the upland portion of the site from the river side of the site. Excavation of bank soils and sediments will occur on the river side of the wall to varying lateral extents and to bedrock in the vertical direction. Upland soils will generally remain in place behind the barrier walls. Removing bank soils and sediments in front of the wall reduces the stability of the wall, but backfilling in front of the wall increases the wall stability. Some of the steps that we're going to take to prevent NAPL from moving into the river, so plugging the pipe penetrations within the existing wall and adding that ISS barrier wall extension, those are going to serve to increase the hydraulic head behind the wall, so have increased groundwater height behind the wall. This is going to exert a greater force on the barrier wall and serve to destabilize the wall. So in sum, we have a few different factors that can serve to stabilize or destabilize the barrier walls for all 3 of these sections. So here we have some photos of what the existing concrete retaining wall looks like now on the lower left. On the right, there's a photo of what it looked like during construction and a typical design drawing of that retaining wall. We didn't have a ton of information available regarding the construction of this wall, so we had some design drawings that were from around 1913 to 1916, but no as-built drawings, and there are also some photos taken during construction. Because the wall condition was so unknown, we had to kind of look at these design drawings and photos to see how the wall was actually built and just get an overall idea of how it was constructed in lieu of any as-built drawings. The wall is assumed to act only as a facade, and again, sediment removal in front of the wall and the increased groundwater head behind the wall are going to result in decreased stability of the wall. So there's going to need to be repairs to the wall to ensure that it remains in place during construction. On this slide on the left, we have another photo of what the wall looks like today, and on the right is another photo of the wall during construction in the early 1900s. So in order to repair the wall, we're going to be using a technique called soil nailing. This is a technique used to stabilize natural or man-made slopes by inserting slender reinforcing elements into the slope. An image showing what these typically look like is on the left there. You've probably seen these a lot at highway road cuts. At West Station, there are going to be several rows of soil nails installed through the existing concrete retaining wall. So the image on the bottom right shows a really rough idea of what that's going to look like, where there will be several rows of nails and they will all be relatively closely spaced to one another. A simplified diagram of a soil nail is shown on the upper right. These consist of grout and steel rebar inserted into borings. They're going to extend about 20 to 30 feet into upland fill behind the wall. The lowest row will be above the river elevation when the hydropower dam located downstream of the site is operating. I'll talk about that hydropower dam a little bit more later in the presentation. And we had to use geotechnical modeling using software specifically designed for soil nail analysis to determine the stability of the wall as a result of installing these soil nails into the wall. The barrier wall will be extended by using in situ solidification to construct the wall extension. The ISS barrier wall serves to provide a hydraulic barrier preventing NAPL migration and to provide support for performing bank soil and sediment excavation in front of the wall. The wall will consist of soil and debris mixed with a binder agent. This is going to be determined by the contractor, but is likely going to be Portland cement and blast furnace slag. And the wall will be keyed into the existing retaining wall and to bedrock. This wall represents a cost saving since soils that would otherwise need to be excavated and disposed of off-site will instead be incorporated into the site infrastructure and provide support for performing the remaining excavation work. Groundwater modeling was performed in order to determine how the steps taken to prevent NAPL migration from the upland portion of the site to the river. So again, those are plugging openings in the existing retaining wall and installing the ISS wall extension. How these factors will affect groundwater levels at the site and therefore the hydraulic forces acting on the existing wall and the wall extension. This graph shows hydraulic heads along the existing and the future ISS retaining walls, with the points along the graph roughly correlating to the image below it. Existing conditions are shown in green and future conditions, which are post-construction conditions, are shown in blue. The remedial construction will result in significant increases in hydraulic head behind the wall, and this increase was considered for the design of both the stabilization for the existing wall, so the soil nailing design, and then the construction of the ISS barrier wall. In order to determine what river water levels will be like during construction, a surface water flow model was developed using HEC-RAS. There is a hydropower dam located about 1 mile downstream of the West Station site that's shown on the left on that image there. When this hydropower dam is operating, so when its dam gates are closed, it generates a backwater pool that affects water levels at the site. The graph shows water levels when the dam is operating, so when the dam gates are closed in green, and water levels when the dam is not operating, so when the dam gates are open in blue. Again, on this graph, the points on the graph roughly correlate with the aerial image below. In the most upstream portion of the site, water levels are essentially the same whether or not the hydro dam is operating. But in the downstream portions of the site, water levels are about 3 to 4 feet higher under just median flow conditions when the dam is operating versus when it is not operating. And this is an even more significant difference under flood flow conditions. Knowing the range of water levels that may be experienced during construction is important for determining how the in-water work will be performed. Overall, for this design, we had several different types of modeling that were performed and an interdisciplinary team consisting of civil and environmental engineers, geotechnical engineers, and hydrologic and hydrogeologic modelers, among other specialties that went into developing the remedial design for this site. Sediment excavations are likely to be conducted in the wet. This is especially true if the hydropower dam is operating at the time of the remedial work. In order to safely perform the in-river work with water still within the river and effectively manage turbidity and sheen generated from the work, diversion barriers will be placed within the river upstream of the work area and parallel to the work area at the location shown in orange on the aerial image. The diversion barriers are going to serve to isolate the sediment removal areas from flowing water by reducing velocity, but they're not intended to be watertight. So within those work areas, there is still going to be water, but it will be flowing at a much reduced rate compared to the river outside of those barriers. These barriers are also designed to overtop during flood conditions. The structure of these is going to vary a bit depending on what the contractor elects to put in place, but they're most likely going to consist of riprap placed on top of the riverbed to form a causeway structure. And then on top of that riprap, there will be concrete blocks anchored to one another. These blocks will have silt curtain and oil boom anchored to them to prevent turbidity and sheen from leaving the work area. So one important factor of the remedial design was considering the construction sequencing at the site. We'll start by placing the diversion barriers. This has to be done first to allow for effective work on the river side of the site. Next, we will repair the existing retaining wall by installing soil nails. Next, we will excavate in front of the existing retaining wall. This will be done after the repairs have occurred so that the destabilizing effect of excavating in front of the wall won't be as prominent of a factor. Next, we will restore in front of the wall. So restabilize by placing material back in front of it. Then we will install the ISS barrier wall extension. This is the really key part of the sequencing here. We need to make sure that we have restored in front of the existing concrete retaining wall before installing the ISS barrier wall. This is because installing the ISS barrier wall will result in increased groundwater levels and increased hydraulic head behind the concrete barrier wall, which will serve to destabilize it. So we don't want to have the condition where the wall is destabilized both by having material in front of it removed and from increased groundwater head behind it. So therefore, we need to restore in front of the wall before adding the ISS barrier wall extension. Next, we will excavate in areas A and B. That will occur roughly from upstream to downstream. We will restore both of those areas. We'll take out the diversion barrier and complete restoring the site, including adding the soil cover. So next, I'm going to talk about the Saranac Street former MGP located in Plattsburgh, New York. So this site is also undergoing remediation under the State Superfund program. It consists of 3 operable units or OUs. OU1 consists of the upland portion of the former MGP area and a portion of the Saranac River that is immediately adjacent to that location. OU2 consists of the Saranac River downstream of Broad Street to the boat launch located on Green Street. That's going to be the focus of this presentation, and it's also the area shown on the image on the right. OU3 consists of the Saranac River downstream of the boat launch and a portion of Cumberland Bay within Lake Champlain. So some alternative field techniques have been employed at this site in order to locate bedrock and observe sheens. Vibrocoring and probing are 2 commonly used techniques during remedial investigations at sediment sites. These methods can be used to gain analytical data as well as to locate bedrock and sheens, but they can be difficult to perform in areas with coarse sediments like gravel and cobble. A couple of alternative methods that were used at Saranac Street that can help to provide more accurate information on where bedrock and sheens are located are test pitting and driving sheet piling. These are more likely to get through coarse sediments to bedrock to give you more accurate results. And test pitting may allow for viewing sediment or bedrock surface. Some drawbacks of these, though, are that you're not necessarily going to be getting analytical data from these methods, although you can locate sheens from them. And you have to bring some larger equipment into the water body. So these images here are showing a PORTADAM diversion system. I'm going to talk about a few different diversion systems that have been used at the Saranac Street site. The PORTADAM system consists of welded rectangular steel A-frames with a geomembrane suspended between the frames, creating a seal. And this allows for water to flow within that sealed off area. Some benefits of this type of system are that they can allow for complete dewatering of a work area, even within flowing waters. They can be relatively cost effective compared to sheet piling, and they leave the subsurface undisturbed, so they don't require subsurface penetration. But some drawbacks are they don't allow for as much flexibility within the field as some of these other methods that I'll discuss. They may not allow for extremely high flood flows and overtopping events. So at Saranac Street, this diversion system was destroyed during an extremely large flood event. So that's a potential drawback of this system. Another system is a sheet pile and concrete block diversion system. In this system, the sheet piling provides the impermeable barrier preventing water flow into the work area, and concrete blocks allow for additional structural stability. Some benefits of the system are that you can completely dewater areas within flowing water. The system is extremely hardy and can withstand very high flows if it's properly designed. And it allows for flexibility based on field conditions. A drawback is that the system requires a till or clay confining layer to tie the sheet piles into. So if you have a system where you just have cobble directly over bedrock, this might not be a system that will work at your site. Next system is an aqua block and concrete block diversion system. In this case, the aqua block and the geomembrane liner prevent the flow of water, and the concrete blocks provide structural stability. Some benefits of this system are that you can completely dewater areas within flowing water again. It allows for a large amount of flexibility within the field, and it does not require a till or clay layer to tie into. So if you have a system where it's just cobble directly over bedrock, this could be a system that might work for you. Some drawbacks, though, are that this can be more expensive than some other methods and can be more time consuming to set up than some of these other methods. Areas within a riverbed where NAPL has accumulated may require some additional work during excavation to completely remove all of the impacted material. Knowing about these areas beforehand can help with ensuring that you're prepared for full removal within these areas, and can also help you make sure you're keeping sheens from migrating outside of the work area. These areas of accumulation can result from both natural and man-made structures. Some natural characteristics or structures of bedrock, such as angled bedding planes or fractures within the bedrock, can result in areas of accumulation. So on these examples shown here, the surface or the bed of the river is moving from one layer of bedrock to the next, and that's creating a kind of pocket where NAPL can accumulate in place. You can also get this effect from some man-made structures, so historical structures like dams or outlet structures. In addition to allowing for NAPL to accumulate within those areas, that can also cause a difference in subsurface conditions that may affect other work you're doing. So on the lower left here, this is an example of where a diversion barrier design was adjusted within the field to account for that dam structure shown. So multiple concrete blocks were placed in the lower portion of the riverbed, and only one layer needed to be placed on the upper portion. It's important to research historical structures and conditions early on when investigating and designing remediation, so you can be prepared for these things you might encounter before you get into the field. If this isn't possible, so maybe if you weren't involved in a project until the construction phase, designs that allow for flexibility based on conditions encountered in the field are valuable. So, and I'm going to talk about some just different considerations for turbidity and sheen management for working within the river. One good way to think about your overall turbidity and sheen management system is to consider the overall physics of the system and think about the balance of flow into and out of the system. This is especially important if you're looking at a system where you don't have a completely watertight structure and you're working within the wet. You need to make sure that if water is coming into your system, there's also an area for water to leave the system, because if you or just allowing it to enter and not leave, you can build up water over time. One way to help manage this is to have multiple containment cells. So in this example, there are earthen berms within the overall area. This can help you manage where you're allowing water to leave your system so that you're just allowing water to leave and not turbidity or sheen. You can also place multiple layers of silk curtains and oil booms to help make sure you're capturing any and all turbidity and sheen. An upstream silk curtain can also help prevent turbidity from leaving the system on the upstream end. And you can also use flow outside of the work area to help contain turbidity. So this slide is showing a good image of how the upstream silk curtain can help to keep turbidity within the work area. So water is flowing from upstream and exerting pressure on the curtain. That's keeping water and turbidity from flowing out on the upstream side and just helping to trap turbidity within the work area. Then this slide is again showing the overall work area. This is during backfill and restoration activities. Even though this is working with clean fill, it's still really important to consider how turbidity is managed because backfilling activities and clean fill can still generate turbidity. That can be a problem. In this case, on the corner of the work area, there's a gap between two of the layers of silk curtain that's allowing some flow from upstream to get into that silk curtain area and help drive any turbidity that is getting out of the first layer of silk curtains towards the bank, just to help prevent it from getting out into the river and within the multiple layers of silk curtain. There are also some important safety considerations for working near public structures. At the Saranac Street site, some bridges had to be shut down during construction. This was managed by engaging with the public through multiple means. So there were press releases talking to the local municipality. Workers at the site would also talk to people who frequented the bridge. So in the days coming up to the bridge closure, come up to people and just let them know that the bridge is going to be closed so that they don't just show up one day and are surprised by the closure. The municipality was also informed of the worst case timeline for completing the work, so that if there was any delays during the work, the municipality would be prepared for the full possible length of closure. In this case, it ended up being performed pretty quickly, but just communicating the worst case scenario helps to ensure that the expectations of the municipality are managed. Finally, I'm going to talk about some conclusions and lessons learned. Sediment remediation projects require synergy between the sediment and upland components. It's important to consider both the sediment and upland components of the overall remedy and how these two areas may affect one another, particularly during design. It's important to sequence work to avoid combining loads. So the example in this case is for the barrier wall at West Station. Work needs to be sequenced so that we don't have the combined load case of increased groundwater head and removed sediment in front of the wall at the same time. River systems can have multiple potential operating conditions, and these all need to be considered. So for working within a river, you need to consider water level, among other factors. Historical structures like dams and retaining walls can be difficult to evaluate. In order to help mitigate the uncertainty associated with this, conservative design assumptions can be used. It's also important to research historical structures early on in the investigation and design process. That will also help to mitigate any uncertainty. And a few other just kind of tips and lessons learned. Consider alternatives to some of the most common methodologies, both for actually performing the remediation and for investigations. Allow for flexibility based on field conditions in your design where possible. Consider the overall physics of a turbidity control system. And when you need to communicate with the public, do this early and frequently. I'd like to thank our client Avangrid and its subsidiaries Argini and ISAG, and thank my Parsons colleagues that have been involved in these projects. Special thanks to Mike Flynn, who's been the CM at Plattsburgh and helped me a lot with the Plattsburgh portion of this presentation. And with that, I can take some questions.
Thank you, Kristen. That was a really interesting presentation on both the history and the challenges of MGP sites. If there's any questions, you can enter them into the chat now and we'll read them out, or you can raise your hand and we will call on you to ask it live. A link to the PDH form has been posted a couple times in the chat feature. If you have any issues downloading that form, if you want PDH credit, just please contact us. So I see we've got a couple questions in the chat already. From Matthew Colbert, what permits are typically required for these types of projects? Are there any unique challenges associated with the permitting process for these MGP sites?
Yeah, so there's quite a suite of permits that are required for working within a river. On the federal side, you'll typically be working under a nationwide permit for a remedial cleanup. It's often going to be nationwide permit 38 for the cleanup of hazardous and toxic waste. You'll also need permitting under Section 10 of the Rivers and Harbors Act, which governs construction within navigable waters, and Section 404 of the Clean Water Act, which states that the U.S. Army Corps must approve of discharge of dredged or filled material into waters of the U.S. You also might have to do evaluations by the U.S. Fish and Wildlife Service to check for endangered species, and the National Marine Fisheries Service, which is a part of NOAA if you're near a marine system. Through the state, there is the Clean Water Act, Section 401, Water Quality Certification, Speedy's General Permit for stormwater discharges. So you'll likely have to develop a SWIP for your site. There's also a review through the State Historic Preservation Office and the Natural Heritage Program, which typically is looking for endangered species or special natural communities. There'll be waste transporter permits through the state if you're taking material off site. And then for some local permitting, you might need a sewer use permit, site plan or building review through the local municipality. There might be special permits for working within a floodplain or working within a right-of-way. So yeah, quite a few different things that need to be checked. One kind of unique challenge for West Station was the DC has recently updated some requirements for evaluating mussel impacts at sediment sites. And this changed when we were kind of partway through our permitting process. So just kind of a new thing we had to learn how to navigate.
We have another question from Robert Condon. At the West Station site, the concrete diversion blocks were shown being placed on top of riprap. Why was the riprap needed? And does the riprap need to be disposed?
So for the disposal component, we're generally going to be placing the riprap back within the site to use it as restoration material. So that's kind of providing some extra sustainability with this project. In order to have the concrete blocks as high as we needed them, we needed to have those causeways in place to make sure we had the blocks up above the river level.
Next question is from Ann Salazar. What did the remedy consist of at the upland portion of the Saranac Street site?
Yeah, so that also consisted of excavation of soils and sediments and some offsite disposal and restoration of the riverbed that was within that OU1 portion. There was a tar lagoon that was excavated and some other areas where coal tar had caused impacts were excavated. There were also NAPL collection wells installed.
So our Q&A through the chat is very popular today, but please feel free to raise your hand and we'll call on you if you want to ask it live. The next question is from Lisa Gordon. How was aqua block material managed after remediation was completed, specifically removal and disposal?
You know, I don't know that one, but I can check on that and get back to you, Lisa.
Okay, next question is from Chance Asher. Was climate change included in the remedial designs? For example, more severe flooding that may impact the sediment remedy, groundwater levels, etc.
Yeah, so as far as the climate change kind of green remediation stuff that was considered, we had a green remediation spec for West Station that states that we're going to minimize idling of trucks, take some other sustainability actions. For the as far as future flood risk, that was just done through a factor of safety for the material that we'll be installing back within the river, just to make sure that it can withstand any future floods.
And we've got one more question right now from Niall Henshaw. At West Station, were other methodologies besides soil nailing considered for stabilizing the existing retaining wall? What were the reasons for selecting soil nailing?
Yeah, so there were a couple other things that were considered. One was external bracing in front of the wall, but this would potentially lead to some obstructions during the dredging activity since we'd have something external to the wall sticking out from it. We also looked at having more widely spaced anchors. These would be larger and would each exert a greater force, and there would be fewer of them compared to the soil nails. Since we don't have a good idea of the conditions behind the wall and there might be voids or blockages behind the wall, we wanted to go with that smaller, more frequently spaced nail so that if one individual location ends up not being able to be placed, it's less of a big deal. So going with the smaller, more frequently spaced nails just allowed for greater flexibility.
And I see Christy Diller you have your hand raised. You can go ahead and unmute yourself and ask your question.
Hey, Kristen. Thanks for the presentation. And I was curious, I've not done much work in New York or in the Northeast, but since you were especially working in the water, did you have seasonal considerations? Like, were there better times of the year to be working in the water, say, trying to avoid a rainy season?
Not so much a rainy season, but during really cold periods during the winter, that can be challenging. Yeah. So there are safety considerations in working within the water if it's extremely cold, and then also if you have any issues with ice, that's something you also have to consider. Yeah. So more just the winter months. Yeah.
Yeah, understood. Thanks.
If there's any more questions, feel free to, oh, there we go one. Scott Hartzell, please, let me see if you can unmute yourself. 1 second.
Hey, Kristen, great presentation. Thanks for all that. Can you talk any about how mature is this market? There have been MGP remediations going on now for a long time. And you said there were like 3,000 around the country and 300 in New York. Where are they at? Are they still in the design phase for the most part, or are they pretty much done?
Yeah, so I'm more familiar with New York State specifically, as opposed to nationwide. But within New York State, there are sites at pretty much all phases of the process. So there are some that are still very early on in the investigation phase, and some that have been completely remediated. I think it's a relatively smaller portion that have been fully remediated, but very many of these sites have been entered at least into some stage of the process and are being worked on to get remediated.
Okay, thanks.
If there's any more questions, again, feel free to enter in the chat or you can raise your hand. We can go to the next slide in the meantime, give people a few more minutes for questions. So our next webinar will be on April 12th at 12:30 Eastern. A preview presented by Jim Schutz on unraveling complexity through fate and transport, numerical simulations in a tidally influenced density-driven flow regime. So hopefully that's got everyone very interested for what will be, I'm sure, a very interesting presentation on a very complex site. For anyone who didn't get the PDH form, the link is in the chat. Please let us know if you were not able to access it. I think if there are no more questions, then we will wrap it up here. Thank you to everybody for joining us today, and we really hope to see you again in April.